expected value of gx is similarly integral gx fxx dx. So this gives us all this. So these are called central moments centered around the mean. These are non-central moments, just centered around the origin. N equal to 1 will give you mean. Here n equal to 2 will give you the variance, right? And then third order moment, etc. So the variance, so this is also mu, or x is just to denote the random variable. Okay. So mu x squared is expected value of x minus mu the whole squared. But remember, I developed this formula. It's a second moment minus mu squared. So you can use this or directly compute this. So let's do it for the Gaussian. Let's say density function is like this. I purposely changed this to different numbers to see. So question is, what is its variance? So variance is expected value of x minus mean. What's the mean of this? Anybody? We just went through this. Mean is mu. So, or if I had b here, mean is b, right? Squared. So we need to compute this. So I'm going to substitute by definition. So this is 1 over 2 pi a squared x minus b the whole squared e to the power minus x minus b the whole squared. First of all, just let me make a simple substitution: y equal to x minus b. When x is minus infinity, y is minus infinity. Same thing with plus infinity. So this thing simply turns out to be So look here, first observation is the mean has nothing to do with the variance. Look at that in the formula. So we just need to compute this quantity because dx is dy, right? So now there are multiple ways to do this. Let me show you one way. So what is the answer to this? Anyone? Look at this. All I did was I removed this. So this is just the area under a Gaussian density function. Right? So this is 1, right? You can write another line. I am going to bring this constant here. So this is, remember this is square root of a squared. So just to save space and time, I'm going to bring that a here. So this is true, right, as an identity. Remember, the reason is I have a y squared here, so question is how do you integrate it? Multiple ways you can do. I'm going to show you one way. Now take on both the sides, do the derivative. This is an equation in A. So take both the sides, a derivative with respect to A. Because these are for finite integral, you can take the derivative. So derivative on the left side is with respect to A. That's not hard, right? That's 1. How about the right side? I'll write the constant. Then what do you get? Anybody? What's the derivative of this with respect to A?
Itself and multiplied by.
Multiplied by? What is the derivative of this with respect to A?
The denominator is A cube minus a cube and minus 1 over 2 behind, in front of it. Below, exactly.
Okay, he says so, so we'll put it this way.
Yeah.
All right, so so minus minus becomes plus. I'm going to take this A and plug it in here. So this turns out to be any mistakes? Anybody? What's the mistake?
I mean,
All right, let me see. The derivative of
a square is like extra. The first 2a square is like not necessary.
here?
Yeah.
Of course it is. This is this.
We already put it on the 2a cube.
Right. So this is, let's do it again. So this is minus y squared, that's true, right? Then the derivative of 1 over minus y squared by 2. The derivative of 1 over a squared with respect to a, what is it?
Minus 1 over 2a squared.
A to the power minus 2, the derivative is?
Minus 2 a
Right? So minus 2 over a cube, right? E to the power minus y squared over 2a squared dA. dy, right? All right, so minus minus plus, this 2 cancels. So this is now, I'm going to pull out an a squared outside. And then I have minus infinity to plus infinity, 1 over square root of 2 pi. There is an a here, I'm going to put it here as a squared. And this 2 and this 2 gone, so I have y squared. And e raised to minus y squared over 2a squared dy. Right? This is equal to 1. So this equal to this, 1 is equal to this. So I can take this a squared, and if you want, I get a new identity. Yes? Remember, 1 is equal to 1 over a squared multiplied by all this. That's the same as writing like this. But this is what we wanted to compute all along. Look at here. So answer is this is a squared. You go home and see whether I made any mistake. So what is the whole point? Whatever you see here, this is the variance. This is the variance in a Gaussian. This is the variance. So generally you would see it like this, sigma squared. So this is sigma squared. That's the variance. I don't want to write sigma squared equal to sigma squared. That's why I brought in a. But the parameter you see here is the variance. This plays no role in the variance. Remember, variance is like mean squared error for the random variable. So there are other ways to compute variance. I just showed you one method. Any questions on this? I mean, this is what I meant earlier, just a little bit integration, etc. You brush it up. What is it? What is your question? What is that you didn't understand?
Firstly, the left of the equation is initially to be a, right?
A here. When you take the derivative with respect to a, it becomes 1. Then you take the derivative, which is what we did here. So then we got 1 over a squared here, right? And we still had 1 here. And you take the a squared there, but this is the expression you want to compute, so that turns out to be. So let me do it for Poisson. Okay, this is good. So remember, if x is Poisson, probability of x equal to k is e raised to minus lambda k over k. This is where we start, k equal to 0, 1, 2, 3. So let's say you want expected value of x squared. So we'll compute what is expected value. We already computed expected value of x. What is it? Anybody remembers? Lambda. So I'll show you one way to compute this. So what's the value of this? Anybody? If I take the probability of, they said it's probability of x equal to k. If I sum up from 0 to 1, 1. This is equal to 1. So I'm going to take, this is the same as I can rewrite this as this. This is an, I took the e raised to minus lambda to the other side. So look at here, this is what is that way. So this is going to be summation k to the power n, probability of x equal to k. This is what we need to compute. K goes from 0 through infinity. So this is k equal to 0 through infinity, k to the power n, e raised to minus lambda, lambda to the power k over k factor. See, this is going to be the hard part. How do you compute this? So I'm going to show you a quick way here. So look here. On this equation, let me take the derivative with respect to lambda on both the sides. So what's the derivative? If you do derivative once, what do you get here? Anybody? Remember, derivative is with respect to lambda, so you get this, right? And the other side? What?
Lambda is
E raised to lambda, right? Now look at here. Well, if you multiply by lambda on both the sides, what happens here? I'm just going to multiply by lambda on this side. So I should multiply by lambda here. What? That's the same as? So this is an identity. Okay. Do it one more time. Take the derivative again. So you will see what I'm trying to do. What will be the derivative again? Anybody? K squared lambda k minus 1 over k factorial equal to, you have to do the derivative here. Yeah, right. So this is, what is the derivative here? 1? Oh, so e raised to minus lambda plus lambda, right. But look at here, this is exactly what you want to do for expected value of x squared with the n equal to 2. So n equal to 3, you keep doing it, but let me take n equal to 2, that's all I wanted here. So for Gaussian, not Gaussian, for Poisson, this value is, remember, so if I multiply by e raised to minus lambda outside, like here, this will, I'm going to multiply this with e raised to minus lambda. So the answer turns out to be, what do you get? Did I miss something? Let me see. What is it? So we already have e raised to the expected value of x to be, we did it earlier, right, is lambda. So expected value of lambda squared is, did I make any mistakes here?
Forgot multiply the one lambda
Where is that?
in the last equation. Still lambda to about k minus 1.
Oh yeah, right. So that's the, so this is fine, this is going to be 1 plus lambda. Then he is right. If you look at this here, this should need to be lambda to the power k. So I'm going to multiply by lambda on both this sides. So 1 plus lambda, I'm going to multiply by lambda. So that this will become lambda to the power k. Here k factorial, k squared, summation k equal to 0 through infinity, e raised to minus lambda. But look, this is exactly what I wish here. So I have the answer to this. This is lambda plus lambda squared. Right, so now I can plug it into here. So this is lambda plus lambda squared minus lambda squared. So the variance of a Poisson variable also turns out to be lambda. So I'll show you another way to compute this. So you can use this to compute all the higher moments of Poisson random variable. Let me show you, give you another formula to compute Poisson random variable moments. So let's say this could be a homework problem. X is Poisson. What is expected value of x3 or x4? So any Chen in this class? Chen's formula? So for a Poisson random variable, this is true. So let me prove the theorem first, then we will use this to compute. So you should be able to do x cubed, x4, everything using this. This is an easy. Or you can use what I did earlier. So remember, this is not, it's only good for Poisson. Chen is only good for Poisson, right? Only for Poisson. So let's start from the left side. This is x multiplied by gx. I'm first proving this formula itself. So this is summation x multiplied by gk multiplied by probability of x equal to. Right, by definition, k goes from 0 through infinity. So this is summation k gk e raised to minus lambda lambda k over k factorial. Again, the same argument. When k is 0, there is no contribution. So k goes from 1 through infinity. K cancels. What do you get? K minus 1 factorial. I'm going to call this equal to m. So k is m plus 1. So this summation now becomes g of k. K is m plus 1. E raised to minus lambda. Lambda to the power m plus 1 over m factorial. M goes from 0 through infinity, right? Because k is, m is k minus 1. K is 1, m is 0. But look at this. This formula is almost like this. Because this is probability of x equal to m plus 1, right? So because of this plus 1, I'm going to take it outside. I'm going to put it outside here as lambda. Then this whole thing reads now expected value of g of x plus 1. Right? And that's the formula. G of x plus 1, not minus 1, x plus 1. Okay, so I proved the formula. Let me now use the formula to find all the means, variance, etc. So I want to find out expected value of x. What should be gx? Anybody? Gx should be, in this case? I should take gx to be what? To apply the formula. X is here, so gx should be 1. Right? So this will be, answer is here, because expected gx is 1, gx plus 1 is 1, expected value of 1 is 1. So we get this formula to be easily. So let's do expected value of x squared. So that I can write it as expected value of x multiplied by x. So gx is x, right? So according to Chen's formula, it is expected lambda multiplied by expected value of g is x. So gx plus 1 is gx is x. Alright, so that's x plus 1. But so this is simply lambda multiplied by lambda plus 1 because expected value of, right? Same as before. So let's do expected value of x cubed, then I'll stop there. Right? So that I can write it as expected value of x multiplied by x squared. So gx is x squared. So this is lambda multiplied by expected value of how? Gx is x squared. So gx plus 1 is
X plus 1 squared.
so that if you expand it is expected value of x squared plus 2x plus 1. So that's going to be lambda multiplied by expected value of x squared plus 2 multiplied by expected value of x plus 1, right? We just did this. X squared is what? Expected value of x squared is lambda plus lambda squared. This is 2 lambda plus 1. So this is going to be lambda cubed plus 3 lambda squared plus lambda, etc. So you go home and find the 4th moment, 5th moment, 2 more moments.